Hello, welcome to Lecture 12. In this lecture, we're going to start a new chapter, and it's still about electric fields, but it's a new way to approach things. In this chapter now, we're beginning chapter 24, which is all about Gauss's law. Students, I would say, tend to find this the second hardest part about Physics 1051. The first hardest tends to be using the line integrals to calculate an electric field. Hopefully you were okay with what we did there in the last chapter. And now we're going to move on to Gauss's law, which is also about finding electric fields. It also uses integrals, but in highly symmetric situations. The integrals themselves are not going to be that difficult. These will be things you know how to do from your calculus class. The hard bit is putting together the math of doing an integral with the physical meaning behind all of the things that we're talking about. I'm going to try hard to stay clear. Your part will be to do the practice and let me know if you're confused. Because Gauss's law relies so heavily on the symmetry, let's just do a quick recap of the different configurations of charge we looked at already and what the electric fields around those charges look like. So here's a PhET simulation of a positive point charge. The electric field points radially outwards. It's strong in close to the charge and it's weak when we're far away from it. If this were a negative charge, we'd still have those radial fields, but it would point inwards. The next configuration of charge we'll look at, we'll do a reminder of, is the line of charge. A line of charge is a continuous charge distribution, which is what we get when we put a whole bunch of point charges all in a row. When we looked at the symmetry of that situation, we saw that the electric field points straight out. And when we have an infinitely long line of charge, then it points straight outwards everywhere. If it's a finite length, then you get some funny stuff at the ends, but we'll stick with infinite lengths. We also looked at the plane of charge. If you wanted to simulate that on PhET, it actually looks just like the simulation for doing a line of charge. The difference is now you're imagining our line of charge becomes a two-dimensional plane where one dimension comes straight out at you. What we know about the electric field there is that it's perpendicular to the plane and it's constant everywhere at all distances. And then the last one we'll talk about, we didn't go through this in the last chapter, but we can also look at a sphere of charge, and this is what I'm trying to model here with my point charges. If you have a sphere of charge, then you have spherical symmetry. So your electric field points radially outwards everywhere. So if you have a sphere of charge, the electric field lines that you drew would look like the electric field of a point charge. So a sphere of charge has an electric field that looks like the electric field of a point charge, radially out everywhere. It's strong in close to the charged object, and it's weak as you get further away. By all means, if you want to investigate this on PhET, you can try and just put in a bunch of charges there so that you make a nice little sphere. For a positive sphere, the electric field would point out. For a negative sphere, it would point in. So now here's a picture of what the electric fields look like around those charges. The only one I'll add to will be our line of charge here. It shows the electric field coming out in 2 dimensions, but really it's all the way out in all of the dimensions. So it's radially outward from that line in every dimension. More like this, but that's a slightly messier charge. Same thing is true for the sphere of charge. It's radially outwards everywhere. To get a sense of how to use Gauss's law, what we're going to do is, first of all, let's consider we have some sort of closed surface. What I've got here is a box. So imagine a big cardboard box that's been taped shut. In the vicinity of this box is an electric field. I'm going to draw those electric field vectors. They come straight outwards like this. So left and right on the sides, up and down on the top and bottom. The front, it comes straight out. And in the back, it goes straight back. Can't see that one so well because it's behind the box. And now we ask, and apparently I'm supposed to do this in a pained Brad Pitt voice, but I don't really do imitations. What's in the box? If you look at this electric field situation, can you tell me what's in that box? Maybe hit pause if you're not sure and just think for a moment. Okay, if you think that there's a positive charge in this box and you think that that charge is spherical, you would be exactly right. And you know that's true because the electric field vectors drawn are the electric field vectors of a spherical charge. And since the electric field vectors point out, it must be a positive charge. So there's a positive charge in this box, and that positive charge is either a point charge or it's a sphere of charge. Okay, so what we just did was we looked at the electric field vectors and we answered the question, what's in the box? Let's ask the question again, but this time let's have the electric field vectors pointing into the box. So this time your answer to what's in the box is it's a negative charge, also with spherical symmetry. So negative charge. And it's either a point charge or a sphere of charge. That's because the electric field vectors are radially symmetric and they point inwards. Okay, let's go with a different set of electric field vectors. This time I'm going to have the electric field coming in from the left, points right, and it keeps going and leaves the box like this. Okay, now what do you think is in the box? This one might be a slightly harder question to remember. Let's think about the fact that electric field vectors, they start on positive and go outwards, or they come from somewhere else, either from infinity or positive charge, and they stop inside the box. So does that situation describe what we see here? Do we have anything starting inside the box or stopping inside the box? That would be a hard no for me. So my answer to the question, what's inside this box? I would have to say nothing. Because there's no electric field lines starting inside the box, so there can't be a positive charge in there. There's no electric field lines stopping inside the box, so there can't be any negative charges in there. Now, I'm going to qualify this a little bit. Maybe there's something neutral, so maybe there's a neutron in there. But I would say one of my answers would be that there is no positive charges in here. There's no negative charges in there, so I would say there's no charges in there. Now, what if I ask that question again? What if I still had my electric field like this? Could I get a different answer? Could maybe there be something in the box? Well, how about if I give you a different situation? What if I do put a positive point charge in here, but I also put a negative point charge in here? What would happen in this case? Well, in this case, every charge that went off the positive would go into the negative and it would stop at the negative. So in the previous example, I said there was no net charge in the, or I said there was nothing in the box. Then I qualified it and I said, well, maybe there was a neutron in the box because a neutron doesn't have any charge. So now I'm going to qualify it again and say, well, maybe there's a dipole inside the box. So there could be a dipole in the box. However, whatever happens, there can't be any net charge. And we know there's no net charge because if any electric field lines started in the box and they didn't stop in there, they'd have to leave the box. And that's not what we see here with these lines. Here we see what's happening going into the box and coming out. If everything that goes in also comes back out, there's nothing starting or stopping inside the box, so there can't be any net charge in there at all. Now, before we go any further, let's ask a few questions about the box. So what we did was we looked at the electric field lines in the vicinity of the box. We thought about what we know about electric field lines, and we answered the question, what's in the box? So my first question to you would be, does the box have to be real? Do you actually have to have a cardboard box to answer that question? And my answer to that is no. So the box doesn't have to be real. It's imaginary or mathematical, so it's not a real physical surface. The second thing, that box is actually kind of special and it helps us figure things out, so we do give it a name. and we call it a Gaussian surface. It's important that that surface is closed, and it's named after the physicist mathematician Carl Heinrich Gauss, who did a lot of work about this. Okay, next question. Does our box actually have to be a box? Does it have to be a cube, or could it be a different shape? I would definitely say that no, it doesn't have to be a box. And in fact, it can be any shape at all. And when we draw a Gaussian surface, or we pick a Gaussian surface, or think about a Gaussian surface, those surfaces should match what our charge looks like. So if we had a point charge or a spherical charge, we'd pick a Gaussian surface that was a sphere. If we had a line of charge, a line looks like a cylinder, our Gaussian surface would be a cylinder. So when we do these problems, we're thinking about the electric field and how the electric field is related to the box, and we think about how the electric field lines go in or out of the box. That's a new concept that we call flux, and we're going to talk about that next.